Hello and welcome to this brief demo of MReplayer, a model-based trace replayer of distributed UMLRT models. UMLRT is a modeling language for designing real-time embedded systems with soft real-time constraints. This demo is intended to show features of MReplayer. Before we begin, I am going to take a few moments to talk about what makes MReplayer unique. Most existing trace replayers for distributed systems are using either physical or logical timestamps. However, these approaches turn out to be computationally expensive and usually inaccurate. Whereas, MReplayer neither uses physical nor logical timestamps for ordering traces from a distributed system. Instead, it relies on static analysis of the behavioral models. This technique is used to compute all possible run-to-completion steps and determine control flow and communication dependencies. Moreover, MReplayer employs an interpreter of UMLRT action code to regenerate variable values during a replay. With the benefit of these techniques, MReplayer is able to reduce the sizes of traces significantly, because no longer they need to be annotated with timestamps and variable values. MReplayer actually uses model transformation techniques to create an instrumented version of a user-defined model. Also, the distribution version of Papyrus RT allows us to generate code of a distributed system from the instrumented model. In the pre-processing step in MReplayer, static analysis is performed to extract run-to-completion steps from behavioral models. It also determines the set of all possible consistent orderings. The trace replayer uses the structural model to create a centralized version of the distributed system. MReplayer also has a core engine that interacts with the web server, that allows the user to replay an execution either forward or backward and inspects variable values at any given time. Finally, a trace that has been successfully replayed by the trace replayer is added into a sequence of ordered traces that MReplayer outputs. The example model we will be using for this demo is Dining Philosophers, which is a classic synchronization problem. This model includes 3 philosophers sitting around a circular table, and there are 3 forks, one between each 2 philosophers, and a philosopher needs 2 forks to eat. So, there should be a proper resource allocation strategy to avoid getting stuck in a deadlock. To run the program, first we need to open MReplayer project and execute its graphical user interface, which is located inside the source code directory. By executing the Java program inside this package, MReplayer's control panel is popped up. This allows the user to execute and monitor MReplayer's engines via a simple yet powerful interface. First of all, the user should select a model that is used for replay. Then the user needs to specify a name for the instrumented model that is generated as an output of the automatic instrumentation. And finally, a name for the trace file that keeps collected traces from a distributed system. Now it's time to run MReplayer's engines one by one. First, instrument engine that executes instrumentation scripts to generate an instrumented version of the model. Then we execute trace collect that establishes a TCP port to receive traces from nodes in the distributed system. After that, we need to execute preprocess engine that performs static analysis on the model to extract all run-to-completion steps. And finally, we execute web server engine that creates MReplayer's web interface. Now we can run the Dining Philosophers system that consists of 4 capsules. According to the configuration file, each capsule is associated to one port in our system that is executed by one processor. Now let's see how MReplayer's web UI works. We can simply open the web UI in a web browser. We actually use this web UI to show a centralized version of the distributed system, where each capsule's behavior and their connectors are displayed. In order to start a replay, first of all, we need to choose one consistent ordering from the drop-down list of the control panel and then click the replay button. Now we can use the replay panel in the upper right corner of the web UI to start the replay. Here we can replay the execution step by step and also see the size of collected traces in the left-hand panel. Moreover, MReplayer highlights active states in green and active transitions in red. If a message is sent from one capsule to another, MReplayer turns the corresponding connector to blue, and it shows message's name and its data on the connector. The user can also go either forward or backward in time and retrieve the variable values. That concludes our demonstration of MReplayer. For more information, please visit the MReplayer GitHub page and read our technical paper, Accepted to Models 23rd International Conference on Model-Driven Engineering. Thanks for watching.